Right now, inside this phone, there are more transistors than the stars visible from the Earth with your naked eye. And each one of these transistors switches on and off billions of times every single second. And every single one of them, every gate, every logic cell, all of that exists because of one spatial property of one material. Not because it conducts electricity, not because it blocks it, but because depending on what you do with it, it can do both. I am talking about silicon. And I'm gonna explain you and show you how that works. Not the watered down version, but the real physics behind it. So, welcome to Inside the Chip. If you ever looked up what is a semiconductor, you've probably seen. A semiconductor is a material with conductivity between a conductor and an insulator, which is technically true and almost completely useless. I mean, if you want to understand the physics, the real physics behind it, or more important for us, if you want to design chips. Don't get me wrong, that definition tells you where semiconductor sits on the spectrum, but it doesn't tell you why. And why is the more important question. So let's build this up properly from the ground. Let's start with what you already know. Materials conduct electricity. Insulators insulate. For example, a copper wire will conduct electricity while a rubber won't, right? That's a day one physics, everyone knows that. But here is what the textbook skips, that the range between the conductors and the insulators spans about 20 orders of magnitude. That's not just a spectrum, that's everything that exists all crammed in one single line. Now the real question is, what is about the atomic structure of a material that determines where it lands on that line? Electric conduction comes down to free electrons. In a copper atom, the outermost electrons, what we call the valence electrons, are so loosely bound to the nucleus that in a copper crystal, they essentially form a sea, which is a cloud of electrons that's free to drift when you apply a voltage. Now take a diamond, the carbon atoms, covalently bonded in rigid lattice. Every single valence electron is locked up in a bond. There are no free electrons. If you apply a voltage, nothing moves. Perfect insulators. So conductors have free electrons. Insulators don't. Where does silicon sit? Silicon has 4 valence electrons, also forming covalent bonds in a crystal lattice. Similar to diamond actually. At absolute 0 degree, pure silicon is an insulator. In a single isolated atom, electrons live on discrete energy levels. That's quantum mechanics, you know this. But then when you bring billions of those atoms together in a crystal lattice, something strange happens to those energy levels. What you get is 2 critical bands. The valence band, where electrons sit at the low energy, bound to the atoms, and the conduction band, higher energy state, where electrons are free to move, and between them, the band gap. The band gap is everything. It's the energy cost of an electron to jump from free to stuck. That's just one single number determines if a material is a semiconductor or is a conductor or is an insulator. At room temperature, the thermal energy available to an electron is about 26 millielectrovolt. Silicon's band gap is about 1.1 electrovolt. That's 40 times bigger, but it's small enough that a statistical toll of electrons has enough energy to make the jump. In a diamond, that gap is 5.5 electron volt, not happening at room temperature. Here is something that trips people off. When an electron jumps to the conduction band, it leaves something behind. A missing electron in the valence band. We call that a hole. And here is the weird part. That hole behaves like a positive charge carrier. It's not real, it's an absence. But it moves through the crystal as neighboring electrons fall into it, effectively propagating in the opposite direction. This is the intrinsic semiconductor, pure silicon, no additive. Equal number of electrons and equal number of holes, both generated by the thermal excitation in the band gap. So now that you understand the physics behind it, the band gap, the electrons and the holes, and the thermal excitation, here's the question that pops up. Why did silicon win? Because there was actually other contenders. Germanium was actually used to build the first transistors, and also gallium arsenide has a better electron mobility. So why silicon? The kilofiscal silicon dioxide is when you oxidize silicon, you get a native oxide that is one of the best electrical insulators known, that forms naturally, conformally, and is chemically stable. That's the gate oxide in every MOSFET. Without it, the CMOS revolution doesn't happen. Germanium's oxide dissolves in water. You can't build a gate oxide with that. Gallium arsenide has no native oxide at all. Silicon's chemistry was uniquely suited for what the industry needed. So where does this land us as chip design? Let me connect the dots. Everything that I show you, the band gap, the electron-hole pairs, and the whole silicon dioxide, all of that are physical constraints that are actually being examined in the industry. When I open a PDK, a process design kit, and look at the MOSFET parameters, the threshold voltage I see there is directly tied to the band gap of the material, the oxide thickness, the doping profile. It's physics all the way down. The next video is going to be about doping, where we actually take that pure silicon, that intrinsic semiconductor, and slowly add impurities. All of that to show how doping changes the carrier concentration and how it's the foundation to everything we build. So if you've been looking for a channel that actually goes deep down into the hardware, hit the subscribe button, because that's exactly what we are doing here. Every video is going to be about a concept where we go from fundamentals to actually the real meaning behind it, the physics down, all of that to understand chip design. And if you enjoyed this video, make sure to like, comment, and subscribe, and share it with someone who you think this will be useful to. And as for me, I will see you in the next video. Thank you.